In this segment, we'll discuss extrema and fixed points of functions and deal with correspondences later in the course. Now, two of the most frequently used techniques in economics are optimization theory and equilibrium analysis, and the contents of this segment have a direct bearing on both of these. We'll start by showing that the image of a compact set under a continuous function is itself compact, and this will take us to Weierstrass's theorem, which identifies conditions under which a real valued function attains its supremum and infimum. Then we'll define convexity for subsets of Euclidean space, and end by briefly discussing Brouwer's fixed point theorem, which identifies conditions under which a self-map on a subset of Rn has a fixed point. And this theorem can be used to establish the existence of a market-clearing price vector in general equilibrium theory, which you will have encountered or will surely encounter in microeconomics. Now here's the first result we want to establish. Suppose that f is a continuous function and S is a compact subset of the domain, then the image of S is a compact subset of the codomain. Now to prove this, we have to show that if f is continuous and S is compact, then any open cover for the image of S must have a finite subcover. So let V alpha be a collection of open sets that's an open cover for the image of S. Now since f is continuous, the inverse image of every open set must be open, and so therefore the inverse image of every set V in this collection is open in the domain. Now to show this, all you need to do is to establish that every element of S is a member of at least one set in this collection. Now that's easy to do because every element of S must have an image that belongs to at least one set in the V alpha collection, and if you take the inverse image of that set, it'll contain the element that you started with. Now we'll use the fact that S is compact. Since S is compact, every open cover must have a finite subcover, so let alpha 1 to alpha m be a finite set of indices. Now each of these corresponds to one set in the collection of inverse images, and S must be a subset of the union of these finite sets. Now note that if you take the sets V alpha 1 to V alpha m in the codomain, the image of S must be a subset of the union of this finite collection. Now this is not entirely obvious because if you take a set in the codomain and then you take the image of its inverse image, you don't recover the set that you started with. For example, if you take the domain and you take the image of its inverse image, you end up with the range of the function and not the codomain, unless the function is surjective. But nevertheless, it's true that if you take any set in the codomain, let's call it E, and you take the image of its inverse image, you end up with a subset of E. Just convince yourself that this is true, and this is what we need for the claim on the slide, that a finite subset of the V alpha collection is an open cover for the image of S. And so every open cover for f of S has a finite subcover, and f of S must therefore be compact. And this proves the result that we were after. If f is a continuous function, then the image of any compact set must itself be compact. Next, we'll prove the following. Let E be a subset of the real numbers. If it's closed and bounded, then both its supremum and its infimum are members of E. Now to see this, let Y be the supremum of E, which exists because E is bounded, and let's suppose that Y is not an element of E. We'll generate a contradiction and thereby prove that Y is in fact an element of E. Now note that for every epsilon positive, there must exist some number x in E that lies strictly between y minus epsilon and y. If there were no such x, then y minus epsilon would be an upper bound for E, and y couldn't possibly be the least upper bound. Now this inequality implies that every epsilon neighborhood of y contains an element of E. In other words, y must be a limit point of E. Now since E is closed and contains all its limit points, y must be an element of E, and we have the contradiction we were looking for. And we've proved that any closed and bounded subset of R contains its supremum and infimum. Now let's put this together with the earlier result we proved, namely that the image of a compact set under a continuous function is itself compact. If we put these two results together, we get Weierstrass's theorem, which states that a continuous real function on a compact metric space attains its supremum and infimum. Now to see the usefulness of this, think about an optimization problem where a decision maker has a set of actions and associated with each action is a payoff which is a real number. And the problem is to find the action that results in the highest payoff. Now this theorem tells us that such an action exists provided that the set of actions is compact and provided that the payoff function is continuous in these actions. Now consider the convexity of sets in Euclidean space. We say that a subset X of Rn is convex if for all pairs of elements x and y in X, the convex combination of these elements is also in X. And this brings us to Brouwer's fixed point theorem, which states the following. If X is a compact and convex subset of Rn, and F is a continuous self-map on X, then F has a fixed point. In other words, there exists some element X in X that is its own image under F. Now if you recall that for subsets of Rn, the property of being compact is equivalent to the property of being both closed and bounded. What this says is that if X is a subset of Rn that is closed, bounded, and convex, then any continuous self-map on X has a fixed point. Now the proof of this theorem is quite demanding, and we're not going to go through it in this course, but you should verify that each of the requirements of the theorem is necessary. If you drop one but maintain the other three, you can find a counterexample. And in fact, we've already seen one counterexample when we discussed pseudo-contractions. Now remember that all pseudo-contractions are continuous functions, and we've seen an example of a pseudo-contraction in which the domain is closed and convex, but not bounded, and the pseudo-contraction has no fixed point. And you should verify that this holds for all the other requirements. So if you drop the requirement that X is closed, but maintain boundedness, convexity, and continuity of F, you can find a function without a fixed point. And similarly, if you drop the continuity of F, or if you drop the convexity of X, you can find a counterexample. I'll leave this as an exercise and end the segment here.